This story centers on fluorine, walking us through its dramatic 115-year history from 1771 to 1886. It's a tale full of both breakthroughs and tragedy, showing just how wildly reactive this element is. Back then, at least 3 chemists died while studying fluorine, and over a dozen others ended up with lifelong, permanent injuries. The video also talks about how important fluorine is today. It's key to making Teflon, medicines, and all kinds of chemical products. Compared with mathematicians and physicists, chemists don't just need perseverance and a brave spirit of exploration. More often than not, they have to put their safety on the line, and even risk their lives. The story of fluorine is the perfect example. Figuring out and isolating this element cost many chemists their lives. But here's the twist: once we finally mastered fluorine, its compounds turned out to be totally different. Far from being deadly, they're everywhere in our daily life. We rely on them in kitchens, cars, medicine, and countless everyday products. Fluorine has truly become an irreplaceable part of modern life. The great Swedish chemist Carl Wilhelm Scheele was the first to discover just how toxic fluorine compounds can be. Back then, he was studying a mineral called fluorspar, which is mostly calcium fluoride. In his lab, he mixed fluorspar powder with concentrated sulfuric acid, and heated the mixture inside a glass distillation vessel. The reaction created a sharp, strongly irritating gas. When Scheele carefully trapped this gas in a glass bottle, he was shocked to see the inside of the bottle turn rough and foggy right away. He figured out the gas was eating away at silicon dioxide, the main ingredient of glass. He then stored the resulting liquid in containers sealed with wax and grease, and that's how he first made hydrofluoric acid. In his lab notes, he wrote, "This acidic gas fogs glass at once. Breathing it in leaves your throat burning for days, like a constant fire." Scheele was the first chemist to clearly record the dangers of fluorine compounds, and he also suffered serious health issues from working with them. Even so, held back by the limited science and technology of his era, he never knew this acid held a brand new element with an incredibly strong chemical attraction. He never tried to isolate pure fluorine, either. After using electrolysis to isolate highly reactive metals like potassium and sodium, the famous chemist Sir Humphry Davy felt confident enough to take on the tough challenge of finding pure fluorine. Working in his lab at London's Royal Institution, he built an electrolysis device with platinum electrodes, and tried running an electric current through the purest anhydrous hydrofluoric acid he could get. But the experiment ran into huge problems right from the start. The harsh, corrosive fumes from hydrofluoric acid quickly ate away the rubber and cork seals. What's more, the gas produced in the reaction was extremely unstable. During one electrolysis test, his equipment exploded violently. Acid splashed everywhere, and deadly toxic fumes filled the air, leaving Davy severely poisoned. He was struck with terrible coughing fits, sharp chest pain, plus severe burns to his eyes and mucous membranes. He spent months recovering from his injuries. Drawing from his painful ordeal and careful analysis, Davy made a forward-thinking conclusion: this element bonds to other substances with unbelievable strength. Ordinary chemicals and traditional lab methods just can't tear it away from its compounds. If we ever want to control this element, we'll need brand new, far more powerful tools and techniques. Davy's research on hydrofluoric acid was a major milestone in chemistry history. With thorough analysis, he proved hydrofluoric acid was a hydrogen-based acid with no oxygen inside. This directly contradicted the mainstream theory back then, the idea put forward by Lavoisier that all acids contain oxygen. Even with such revolutionary discoveries, Davy never managed to isolate pure elemental fluorine in his lifetime. Back in 1813, 2 French chemists, Joseph-Louis Gay-Lussac and Louis-Jacques Thénard, drew inspiration from Davy's failed attempts and decided to take on the puzzle of fluorine together. They came up with an even riskier, more daring experiment. They mixed dry calcium fluoride powder with boric acid, then heated the blend to extreme temperatures inside a platinum distillation vessel. Their theory was that boric acid could strip fluorine out of its compound. The experiment did create large amounts of a colorless, extremely toxic gas, but right as they tried to capture and study this gas, a leak broke out at the joint of their lab equipment. From the perspective of modern chemistry, the main reaction in their experimental process can be deduced as follows. Steps 2 and 3 were the core reactions through which they hoped to produce fluorine gas. Unfortunately, step 2 could occur at extremely high temperatures, but it did not yield fluorine gas. The main products were boron trifluoride gas and calcium oxide. Step 3 required an extremely high temperature under normal pressure, and the equilibrium strongly favored the reverse direction, making it nearly impossible for the reaction to occur in practical experiments. As a result, they failed to obtain elemental fluorine. Gay-Lussac breathed in way more of the poisonous gas. He passed out right away and stayed unconscious for 3 whole days, fighting for his life. Thenard didn't get it quite as bad, but his lungs were permanently hurt. He coughed for the rest of his life, had trouble breathing, and was never fully healthy again. Later, in their paper, the 2 scientists wrote with resignation and a serious warning, "The isolation of this substance brings with it dangers that are lethal and exceedingly difficult to guard against. Its chemical activity is so intense that it likely exceeds the reach of contemporary chemical knowledge and technology. To pursue it forcibly may demand too great a price." In 1836, 2 Irish brothers, George Knox and Thomas Knox, tried a bold method that you could call fighting poison with poison. They decided to heat mercury fluoride, thinking the strong reducing ability of mercury would help set fluorine free. Working in a poorly ventilated private lab, they gently heated the mercury fluoride in a gold container over an alcohol lamp. But the gas given off by the reaction showed just how dangerous it was right away. The inside of the expensive gold container quickly corroded and bubbled up. Worse still, poisonous gas leaked everywhere. Thomas, who was standing closer to the equipment, got hit directly in the face and eyes. He suffered serious vision damage and nearly went blind. His older brother George kept being exposed while cleaning up and doing more research, so he had to spend 3 years recovering in Italy to ease the health problems caused by the poisoning. Their experimental notes, written in shaky handwriting, recorded, even platinum containers were swiftly destroyed. The destructive power of this substance surpasses all imagination, akin to a flame from hell. In the 1870s, the French chemist Edmond Frémy, who later became Henri Moissan's teacher, carried out more systematic and well-founded research. He tried to use electrolysis on molten salts like calcium fluoride and potassium fluoride, but these salts had extremely high melting points, making the experiments incredibly hard to carry out. After carefully looking into all the earlier failures, Frémy put forward a key idea in 1884 that finally pointed the way to success. To isolate this element, we must use electrolysis in completely dry conditions, keeping it away from all organic materials and most common elements. Even tiny amounts of impurities or water can cause terrible side reactions and serious corrosion. Sadly, after years of research, Frémy's body had built up too much fluoride. In his later life, he suffered severe skeletal fluorosis. His spine and joints began to grow abnormally, harden and even fuse together. In the end, he was paralyzed, confined to bed in terrible pain, and died in great suffering. It was an afternoon in 1886, in the not-so-big lab of the École Supérieure de Pharmacie in Paris. Henri Moissan took all the wisdom and lessons from the struggles and sacrifices of the scientists who came before him, and turned them into a carefully designed setup and a strict step-by-step process. 1. Raw material treatment. First, he took potassium hydrogen fluoride and recrystallized it over and over again with anhydrous hydrogen fluoride to get super pure potassium hydrogen fluoride. Then he heated it in a platinum dish to dry it out completely, turning it into a totally water-free molten electrolyte. That way, water couldn't get in the way, no unwanted reactions, no explosions. 2. Temperature control. He dipped the U-shaped electrolytic tube into a coolant made of chloroform and dry ice, and got the temperature of the whole system steady at exactly -23 degrees Celsius. The low temperature slowed down fluorine's chemical activity and reduced the amount of hydrogen fluoride evaporated, which kept the experiment safe and the reactions under control. 3. Reaction apparatus. He used a U-shaped tube carved from a single piece of fluorspar as the electrolytic cell. The material of anode was platinum-iridium alloy, the material of cathode was plain platinum. In the middle of the U-shaped tube, he put a fluorspar diaphragm to separate the anode and cathode. Fluorspar and that platinum-iridium alloy can stand up to fluorine's erosion, and the diaphragm kept hydrogen and fluorine from mixing together, which would have caused an explosion. Once he turned on the electricity, he could clearly see a steady stream of pale yellowish-green bubbles forming smoothly and non-stop at the anode. Those bubbles rose up along the fluorspar pipe and collected in a platinum container that he had pre-treated with fluorine gas to passivate it. The surface of the container was covered with a tight, dense layer of metallic fluoride protective film. The electrolysis process can be divided into the following 2 steps. The first step is electrolyte preparation and melting. In this step, the electrolyte was completely anhydrous potassium hydrogen fluoride. When heated, it melted and ionized, providing conductive ions. The second step is electrolysis reaction. Under the action of direct current, the molten potassium hydrogen fluoride underwent electrolysis. For the cathode reaction, hydrogen fluoride ions gained electrons, producing hydrogen gas and fluoride ions. For the anode reaction, fluoride ions were oxidized at the anode, releasing fluorine gas. After collecting a certain amount of gas, Moissac conducted a decisive verification experiment, inserting a piece of silicon crystal into the gas. In an instant, the silicon spontaneously ignited in the fluorine gas, bursting into dazzling white flames and forming silicon tetrafluoride. This intense and unambiguous reaction provided irrefutable proof of the existence of elemental fluorine. But the cost of this victory was brutal. 20 years of non-stop, high-intensity research meant Moissac was constantly exposed to low levels of fluorine gas. His teeth had almost all fallen out, his eyesight got really bad because his cornea and lens were damaged, his bones became fragile and easy to break, and both his heart and kidney functions were seriously harmed. In 1906, Henri Moissac won the Nobel Prize in Chemistry for the isolation of the element fluorine and the invention of the Moissac electric furnace. But less than a year after getting that honor, this worn-out conqueror died from multiple health problems caused by chronic fluorosis. He was only 54 years old. From 1771 to 1886, that's 115 years of tragic exploration. At least 3 chemists lost their lives, and more than a dozen others were left permanently disabled. At the Nobel banquet in Stockholm in 1906, standing before the pinnacle of glory, Moissac spoke with profound emotion and gravity. "Permit me to correct a title. I am not the discoverer of fluorine. I merely stood on the shoulders of giants to take the final step, those giants who fell or were maimed before me. The light shining here today belongs to us all, but especially to those eyes that can never gaze upon it again. Fluorides have quietly integrated into every corner of modern life, from strengthening dental health to advancing high-tech industries. Like we mentioned earlier with Scheele's experiments, when fluorspar meets sulfuric acid, it lets off colorless hydrogen fluoride gas. If you looked at that gas under a microscope, you'd see it doesn't float around as single molecules, instead, they hold hands to make long chains. This special hand-holding is known as hydrogen bonding, the strongest intermolecular bond in nature, far stronger than the bonds holding water molecules together. It is precisely this intense unity that allows hydrogen fluoride to etch the hardest glass at room temperature, and to catalyze the most complex reactions in the petrochemical industry. Over 250 years, hydrogen fluoride has come a long way, from etching pretty stained glass in churches to cleaning the chips that power our digital world. It's like a little snapshot of how we've gone from being craftspeople to living in the information age. On April 6, 1938, Roy Plunkett, a young chemist at DuPont, was inspecting a cylinder that was supposed to be filled with tetrafluoroethylene gas. To his surprise, the pressure gauge read 0. Normally, this would indicate a leak, yet the cylinder's weight had not decreased at all. Driven by curiosity, Plunkett saw the cylinder open. Inside, there was no trace of gas, but the interior was coated with a smooth, waxy white substance. What seemed like a failed experiment turned out to be one of the greatest discoveries in the history of materials science: Teflon. You can imagine Teflon as a carbon chain completely guarded by fluorine atoms. Each carbon atom is escorted by 2 fluorine bodyguards. These guards are so diligent that virtually no substance can get close enough to react. This unique structure grants Teflon 3 miraculous properties: absolute non-stick, absolute corrosion resistance, and absolute insulation. During World War II, Teflon served as a classified material for the Manhattan Project, utilized to handle highly corrosive uranium compounds. After the war, it first found widespread use as an industrial sealing material. However, it wasn't until 1954 that a spark of domestic innovation changed everything. French engineer Marc Grégoire's wife, Colette, had a sudden brainstorm: what if we coated cooking pans with this non-stick substance? That question ignited the modern kitchen revolution. Today, Teflon is permeating nearly every aspect of our lives. In the medical field, it is used to manufacture artificial blood vessels, as blood does not coagulate on its surface. In the field of aerospace, it serves as insulation for the wiring harnesses of Mars rovers, protecting them in extreme environments. In the field of architecture, it coats rooftops, providing exceptional resistance against wind and rain. In the fashion field, it makes waterproof yet breathable outdoor jackets possible. In the early 20th century, refrigerators relied on toxic ammonia, flammable propane, or corrosive sulfur dioxide as refrigerants. Leaks were often fatal. In 1928, Thomas Midgley Jr., a chemist at General Motors, was assigned a critical task: to find a refrigerant that was safe, stable, and non-toxic. Over the course of just 3 days, Midgley systematically analyzed the periodic table. He observed a clear trend: flammability decreased from left to right across the table, while toxicity decreased from bottom to top. Following this logic, his gaze settled on the upper right corner, the domain of fluorine and chlorine. Ultimately, he synthesized dichlorodifluoromethane, which would later become universally known as Freon 12. To demonstrate its safety, Midgley performed a dramatic demonstration at a meeting of chemists. He inhaled a lungful of Freon 12 and slowly exhaled it toward a lit candle. The flame was extinguished instantly, yet Midgley remained unharmed. At that moment, the era of the modern refrigerant was born. By the 1970s, global production reached 1 million tons annually. Freon became the heart of refrigeration and air conditioning, and was even used as a propellant in hairsprays and deodorants. However, in 1974, Mexican chemist Mario Molina and his supervisor, Frank Sherwood Rowland, published a mere 4-page paper in Nature. They proposed a startling theory: once Freon reached the stratosphere, ultraviolet radiation would break it down, releasing chlorine atoms. Each chlorine atom could destroy tens of thousands of ozone molecules. Initially, industry giants fiercely opposed this theory. DuPont famously ran advertisements dismissing the ozone hole as science fiction. But in 1985, British scientists discovered a massive hole in the ozone layer above Antarctica, an expanse roughly the size of the United States. The reality was even more terrifying than the theory had predicted. In 1987, 24 nations signed the Montreal Protocol in Canada, the first global environmental agreement in human history. Today, Freon has been largely phased out, and the ozone layer has begun a slow, steady recovery. The significance of this story extends far beyond environmental protection. It proved that when global scientific consensus is reached, humanity has the power to take collective action before a catastrophe occurs. To medicinal chemists, the fluorine atom acts like a magic switch. Its atomic size is remarkably similar to that of hydrogen, yet its chemical properties are worlds apart. The story begins in 1957, with the accidental discovery of an antifungal drug, flucytosine. Once inside fungal cells, flucytosine is converted into 5-fluorouracil. However, 5-fluorouracil proved too toxic to human cells for direct use. It wasn't until cancer researchers discovered that cancer cells behave like gluttonous children, frantically absorbing any substance resembling nutrients. This insight allowed 5-fluorouracil to be deployed directly in cancer therapy. The cancer cells mistake it for nourishment and ingest it, only to trigger their own destruction. Modern fluorinated drugs can even perform targeted navigation within the body. Doctors inject patients with glucose tagged with fluorine 18. Because cancer cells have hyperactive metabolisms, they absorb more of this labeled sugar. A PET scanner then acts like a GPS, pinpointing metastatic lesions throughout the body with remarkable precision. This ability to see cancer cells is revolutionizing oncology. Today, over 20% of modern pharmaceuticals contain fluorine atoms, ranging from antibiotics and anti-cancer agents to antidepressants and anesthetics. In the 1960s, NASA sought new power generation methods for spacecraft. The fuel cell emerged as the ideal candidate, generating electricity directly via the reaction of hydrogen and oxygen. However, this required a special membrane, one capable of conducting protons while simultaneously isolating hydrogen from oxygen. DuPont chemist Walter Groth experimented with hundreds of materials. Then, a breakthrough idea struck him. What if he replaced some of the fluorine atoms in polytetrafluoroethylene with sulfonic acid groups that could conduct protons? Thus, the perfluorosulfonic acid membrane, Nafion, was born. Under a microscope, the structure of Nafion is breathtaking. The robust PTFE backbone forms a durable skeleton, while the sulfonic acid groups spontaneously aggregate to form hydrophilic channels just 2 to 5 nanometers in diameter. These channels act as dedicated highways for protons, allowing them to travel at speeds of several meters per second, while effectively blocking hydrogen molecules and electrons. In 1981, during the maiden flight of the Space Shuttle Columbia, its electrical power was supplied by fuel cells utilizing Nafion membranes. At that time, the membrane cost $10,000 per square meter, more expensive than gold by weight. The turning point came in 2014, when Toyota launched the Mirai, the world's first mass-produced hydrogen fuel cell vehicle. Through 3 decades of R&D, scientists successfully reduced the membrane's cost to 1/100th of its original price. Today, the Nafion membrane inside a single Mirai, when unfolded, covers approximately 20 square meters. It enables a driving range of 650 kilometers while emitting nothing but water. As the world transitions to a hydrogen economy, perfluorosulfonic acid membranes are evolving from specialized aerospace materials into a key technology capable of reshaping the global energy landscape. From space shuttles to residential power supplies, from submarines to automobiles, this transparent film is quietly driving an energy revolution. Every fluoride compound carried an incredible decades-long scientific story behind it. It all started with accidental discoveries, then moved on to in-depth exploration, and finally evolved from a little lab experiment into groundbreaking applications that changed the whole world. The biggest scientific breakthroughs are never just perfectly planned out. Instead, they happen when curiosity, persistent effort, and a bit of good luck come together. Every time we use a non-stick pan for cooking, drive an electric car, or take modern medicine, we're actually connecting with the amazing history of these special molecules.